Good morning, everyone. This is Jake. We are going to get started super quick today. We got an awesome guest webinar presenter today by the name of Chris Wright. He works for Baseline Irrigation Solutions. He's going to be talking about a really neat topic, um, something that is definitely above our heads, and this is why he gets paid the big bucks. So I'm not going to ruin too much of it, but if you guys have questions or comments, we have our chat windows and our Q&A box down in the lower left and right. So please answer or ask your questions over in the left and have any chat going on in the right box there. And we will definitely get to those as they come in. So without further ado, I present you Chris Wright.
Thank you very much, Jake. I'm excited to be participating in the LandFX webinar today and presenting on a topic that is gaining increased notoriety in the industry as more and more applications of green roof and green walls are being installed both nationally as well as internationally. In my experience in the industry and working in this kind of discipline, the question is often asked, how do you properly irrigate a green roof and green wall application? And there are, of course, many opinions on that subject, depending on who you talk to, but utilizing the correct technology and having an understanding of how water moves through such an application can really help to ultimately manage that irrigation efficiently to achieve objectives or to accomplish the aesthetic value that the roof or wall is intended to provide. So I want to start off by talking a little bit about soil structure, because soil structure plays a huge role in a green roof or green wall application, as you can imagine. And when we discuss soil structure, it's important to understand how that soil is made up. And soil is made up of particles, of course, and those particles are identified by their size. And the larger the particles, the more space that is between those particles in that structure. And that is an important concept to understand because water is held between those particles and those spaces that exist. So as we look at different soils that are most common on a site level, we may be working with a gravel to sand to silt or clay type of soil particle, and those different particles obviously have different sizes as illustrated in the scale on the screen. If we look at soil structure as it's commonly referred to, soil is classified based on the relative proportions of the particles in a sample. And we've got the textural triangle where clay, silt, and sand blended together create different soil types. Those soil types may be clay or sandy clay or clay loam. And these soil types are often referred to in irrigation when we're trying to determine how much water to be applied so that the soil structure can absorb and hold that water and provide water to the plant material that's being irrigated. The thing to keep in mind is, as I mentioned before, the water is held between the particles and not by the particles themselves. And in reality, soils on any given site rarely fit in the textural triangle. The textural triangle identifies 70 different soil types, but in reality there's hundreds and hundreds of different soil types that may exist on any given site. And it's easier and more repeatable to be able to measure the amount of water that's being held between those particles rather than guess how much water is being held in that soil structure. When we look at plant water use characteristics, the plants that are planted in different soil mediums are as variable as the soils themselves. And we know that, you plant the same plant in 3 different soils, it may have 3 different water use characteristics. And the same plant planted in the same soil with 3 different fertility levels will have different water use characteristics. And then if we consider the health of a plant, a healthy disease-free plant will have different water use characteristics than a sick plant in the same soil conditions. So there's many things to consider when we're mixing soil structure and plant material. And then once we have that combination, we need to have an understanding of the soil moisture holding capacity, because the plant material is going to rely on that in order to thrive in the landscape. So if we consider the different types of holding capacities, on the far left we have saturation, which means that all of the spaces between those soil particles are full and there's excess water, either in the form of standing water or runoff in that soil structure. Field capacity is really the sweet spot where the soil is holding as much water as it possibly can after gravitational drainage has occurred. And then maximum allowed depletion is how much moisture depletion in that soil structure will be allowed before a replenishment needs to occur in the form of an irrigation cycle. Permanent wilting point and oven dry really don't come into factor when we're making irrigation decisions, but they're important to have an understanding of, especially for us as an engineering company, because they play a role in the algorithms that we utilize to measure moisture in the soil profile. So permanent wilting point would indicate the period when tissue damage is actually happening on the plant material, and oven dry would indicate when all of the moisture has been depleted out of a soil profile and it's essentially just powder. The two that we really focus on when we're making irrigation decisions need to be field capacity and the maximum allowed depletion. So if we were to define field capacity, again, it's how much water can be held in media in the face of gravity. And I like to use the analogy of a sponge because soil works very much in the same way. If you take a sponge and dip it into a bucket of water and let it fill all the pores of that sponge with that water, and you pull it up out of the bucket and it will drain and drip, that is all saturation. Once that dripping and draining ceases, then that sponge is holding as much water as it possibly can between those pores in the medium in the face of gravity. If you were to squeeze that sponge, there's available water there, and much like soil, there's available water in a soil medium that's made available to the plants after that gravitational drainage has occurred. Allowed depletion would be how much media dry down is allowed to maintain plant health or aesthetic value. And if we look at allowed depletion, it's dependent on many different environmental factors. It can change dramatically in a short period of time, and in reality, allowed depletion is the opinion of the landscape manager who is looking to achieve an objective in water use or maintain a desired aesthetic value of that plant material that he's managing. So if we look at field capacity versus allowed depletion, coarse media is going to have a lower field capacity and therefore a tighter depletion than a heavy clay or a tighter soil. So having the ability and being able to recognize the different moisture readings at field capacity for different soil types can help us make better decisions as to how we need to irrigate based on that allowed depletion to achieve our objectives. So as we look at an environment like a green roof, do these same principles apply? Because we know that in a green roof application, we're dealing with engineered media that certainly does not fall within the standard textural triangle for a soil structure. So as we use engineered media, how are field capacity and allowed depletion found for that particular blend? And ultimately, and most importantly, will water be available for the plant material when it's needed in that kind of extreme environment? So if we look at different soils for green roof applications, there's plenty of information available on the web today that give different guidelines for different soil types for green roof or green wall applications. Chuck Friedrich provided some good general guidelines in an article he published called "Don't Call It Dirt," where we want to have about 75 to 80% of the soil media inorganic and 20 to 25% of the soil media actually organic, that would provide good drainage, soil air capacity, and organic nutrient for the plant material in that application. He goes on to identify that there are 6 properties that a good media must possess, one being good drainage and aeration, the water holding capacity, which we've talked about, nutrient holding capacity. That media needs to be permanent. It also needs to be lightweight and sturdy, and must be stable to support the plant material that's been planted in that site. So depending on whether the project is extensive or intensive, the blend of these different medias may alter or change and will be variable. So for an intensive application, you're going to have a lightweight aggregate that's going to be in a little bit smaller proportion to other sand or organics that may be present in that soil profile. And in an extensive application, you're going to need a larger percentage of lightweight aggregate and a smaller proportion of sand and organics in order to meet the needs for the structure as well as the plant material. So if we look at a specific application, one that Baseline has been involved with for quite a while, and we're very proud to be involved with, is a very extensive green roof on the Facebook campus in Menlo Park, California. This is a 9-acre green roof that sits atop the corporate office and was designed with the intention to draw the employees up out of the office environment and give them a natural setting to work in and meet in during the workday. So the green roof itself is park-like. It's very similar to a city park when you're in it and wandering about the green roof, and it's very, very beautiful place to be. This shows you a cross-section of the typical planting medium on the roof itself. You can see that it's very shallow media, typically 18 inches to 24 inches of engineered soil atop the roof structure that the plant material is planted in. And if you take into consideration the soil itself and see that soil profile, and then look at the plant material that it is supporting, it is amazing that that little amount of soil depth can support extensive tree canopies, and extensive plantings that will draw a lot of water out of that soil profile over time. You can see here that not only do we have the added weight of the soil profile, but the plant material itself is extensive in its size and weight as well. So the soil needs to be strong enough to support that type of plant material in wind conditions, to make sure that they're anchored and secure and permanent in that site application. So the technology that is utilized on that green roof at Facebook to help the landscape manager understand how the soil is being replenished with irrigation and made available to the plants is baseline soil moisture sensors. And with the soil moisture sensors, it gives us the ability to measure in real time the amount of evaporation that's out of that soil profile and the transpiration that is occurring through the leaf surface area of the different plant materials. And bottom line, if you don't measure that process, you can't manage to meet the expectations or objectives of that landscape. So how do baseline soil moisture sensors work? Baseline employs and has a patented technology that has really changed the way that plant material is being irrigated. The blade itself that is buried in the landscape is very durable in its construction, and we have removed all contact of metal in the soil profile that will eliminate degradation over time and gives us a more reliable, accurate, and repeatable volumetric moisture content of that soil profile that it is buried in. It's very easy to install. Wires to a 2-wire or conventional wire irrigation system, and we utilize agronomic algorithms in the technology that allows us to have multiple soil moisture sensors on a single controller, and we can program each one of those sensors independently depending on what watering strategy we want to employ. The way the sensor works is there's a embedded wire path in the sensor blade where a pulse of electricity is sent through that wire path, and we measure how long it takes to travel the wire path. And the high frequency pulse of electricity that we send down that wire path has a sphere of influence that extends outside the blade and gets into the soil structure. And we know that when the pulse travels through moisture, it slows down. So the faster the pulse travels, the drier the soil, the slower the pulse travels, the wetter the soil. We're able to take that time domain frequency and put it into an algorithm that gives us a volumetric moisture content of that soil with a plus or minus 1% accuracy. We employ, simple physics with the technology because light travels through air faster than water. So many of you may have done the experiment in school or growing up where you put a pole in a swimming pool and it looks like the pole bends. That's because the light is traveling faster through the air than the water, and it creates that illusion that the pole is bent. So same principles apply in the technology that we're employing, and we're again able to accurately measure the amount of water that's being held between those soil particles and the soil structure. One of the advantages of having this instrument in that soil structure is that it gives us the ability to see applications of irrigation move through the soil profile and the root structure of the plant material. This is a moisture graph of an actual site that we did a study with a landscape contractor in Las Vegas, Nevada, where we were analyzing the irrigation applications and trying to determine how effective those applications were and how long it actually took those applications of water to filter into the soil medium and be available for the different plant material. And in this analysis, we had an irrigation cycle that started at 11 p.m. on the 4th of September. And at that start time, the moisture content of that soil profile was 24.7%. The zone had a 45-minute runtime on it, and when that zone finished watering at 12:27, the moisture content at that time was 26.12. So we had seen an increase in the moisture content, but the moisture content did not peak until 6 a.m. at 32.04%. So it took essentially 5.5 hours for that irrigation application to infiltrate into that soil profile 3 inches to where that sensor was able to effectively see that application of water. So having the ability to analyze the data that's provided by the moisture sensor, we can make better irrigation decisions and determine if we are watering to field capacity with a given application, or if we are overwatering from that application of water and not conserving as much as we could. So the moisture sensor essentially acts like a thermostat in the landscape, where it is monitoring again in real time and providing feedback to the control system how much water is available to the plant in that particular soil structure. And it again is taking into account the amount of evaporation that is occurring at any given time from that soil, as well as how much water is being used by the plant material during that same period. And we can use that information to maintain a desired threshold or level of moisture in that soil profile to meet our needs and or objectives. So the most common watering strategy that is employed with soil moisture sensors is the lower threshold watering strategy. And essentially, the lower threshold tells the system to turn on based on soil moisture and then turn off based on time. And we're essentially controlling the frequency of irrigation cycles using this watering strategy to determine if, when a start time comes up on a irrigation controller, is that application of water really necessary based on how much moisture is in that soil profile and available to the plant material at that given time. This gives you another visual illustration of an actual system that operated in August of 2014, where this lower threshold watering strategy was being used to determine how frequent the irrigation actually needed to happen. A threshold was set in the controller just below 24% volumetric moisture content. Start time was available every day for this system to run, and when the system did run, that zone where the sensor was buried was running for 50 minutes. So you can see on the far left on the 2nd of August, at start time, the moisture level was below the threshold, which is indicated by the solid green line. And we turned on and watered for 50 minutes, and you can see the spike in moisture content as a result of that irrigation application. We then went into a series of rain events where the sensor was able to account for that effective rainfall and subsequently eliminated the need to irrigate on subsequent days because there was enough water in that soil profile and available to the plant material, so those irrigation cycles were not required. So in the month of August, in a very arid climate, where there was thunderstorm activity available, we only watered 6 days for the entire month. Another way that the watering strategy can be enhanced or altered is by setting a threshold where there is a desired moisture content to be maintained. So in this case, this is the same irrigation system a year later, where a desired moisture level of 27% was set as a threshold in the controller, and then the zone on time, rather than having it a solid 50 minutes, was divided into 3 even cycles of 25 minutes. And 3 separate start times were set up in the controller for the given water days, and then the sensor determined how many of those cycles were actually needed in order to get the moisture content back up to the desired moisture level in that soil profile. So you can see on the 2nd of August, 3 cycles were required in order to get up to the desired moisture content for a total zone on time of 75 minutes, but there were several days where 25 minutes or 50 minutes were only required to achieve that moisture level in the landscape. So when we transition from a green roof application or a level site to a vertical site with green walls, how does the technology accommodate this kind of application, and how does the water strategy change? And when we're dealing with green walls and in vertical irrigation applications, there's other things that need to be considered because the water need characteristics are going to change dramatically, because you've got a much shallower soil profile, you've got more extreme conditions where you're having to deal with air movement around the structure that may create several different microclimates that would alter the watering need for the plant material on different sides of the building. And then of course we have to deal with gravitational drainage that is obviously going to occur as you're applying water to that vertical garden. So how does a moisture sensor monitor this? And Baseline has recently released a new sensor that was designed and engineered specifically for green roof, green wall, or container type applications, that has a smaller footprint that fits into these smaller soil profiles or smaller planting areas that can act the same as the sensors that are used in general landscapes to give us a indication how much moisture is being applied and held in that soil profile for the green wall. So in this particular application, the installer wisely zoned the panels in 3 different irrigation zones, top, middle, and bottom, knowing that gravitational drainage is going to occur and the bottom of the wall is not going to need as much water or as frequently as the top of the wall. So we broke this panel into 3 different programs, had a sensor installed in each one of those sections of the panel, and then programmed the controller accordingly. And this gives an illustration of the actual irrigation cycles that occurred on the top, middle, and bottom of that green wall panel that was shown in the picture. So in program 1, which is the top of the wall, there were 4 different start times that were available every day, one at 8:15, 10:15, 12:15, and 2:15. The runtime was 15 minutes. A lower threshold strategy was used where that threshold was set at 24%. And then when those start times came up, the sensor either allowed or did not allow that irrigation cycle to occur, and the manager was able to maintain a moisture level of 24% in that application, which was set to meet the objectives or expectations of the manager. As we look at the middle of the wall, 2 start times were programmed for the middle panel, and the runtime was 12 minutes. And you can see that irrigation was required frequently, but the runtime varied somewhat based on a lower threshold setting of 21%, which is what they desired to have at that part of the wall. And then the bottom of the wall was set up with 2 start times with a runtime of 5 minutes, but because of that gravitational drainage, no irrigation cycles were actually occurring. So they were not applying water to the bottom of the wall just for sake of applying water at a given start time. The sensor was determining whether or not that irrigation cycle was actually required when those start times came up. So in summary, we know that soils vary greatly in composition, and it determines how much water is held between those soil particles, whether it's at grade or engineered on a green roof or green wall, and that will affect how much water is available to the plant. The same field capacity and allowed depletion principles apply to an engineered media, and the technology is advanced enough and sensitive enough to be able to find where that field capacity level is for that given engineered media, and then thresholds can be set based on the opinion of the manager as to how much depletion is able to occur before irrigation cycles are applied. The Wright sensor technology accurately measures moisture content in real time to make intelligent irrigation decisions. So having the ability to constantly monitor how much moisture is being drawn out of that soil profile to see how our application is reacting to different environmental concerns and plant water use characteristics, we can make better irrigation decisions. And of course, we want to maintain a desired moisture content in a green roof or green wall application to maintain health and aesthetic value of that installation. So Baseline on our website, baselinesystems.com, offers many different online resources for the specification community to help you have a better understanding of how our technology works, how to design with it, and then how to specify it on plans for these specialized type applications. So we encourage you to visit us online. Feel free to reach out and contact me as the regional sales manager for most of the western United States. And if you're in other parts of the country, we can direct you to the regional manager that can help you in your design efforts as well for your local area. But again, I appreciate the opportunity to present. I hope this was useful information. And if there's any questions or comments, we'd be happy to address those at this time.
Yeah, we actually do have a few. Daryl has a couple things. The first one's more of a comment, I believe, but just making note that soil-based versus fabric-based green walls will have different moisture profiles. So, keeping that in mind. I don't know if you have anything to expand on in that realm, but
As long as the moisture sensor is able to have good material contact to that media, whether it's soil or fabric, we will be able to measure the moisture content being held in that different media. So obviously the graphs will display differently, and field capacity and depletion settings may be different for a fabric-based application, but if it's holding water, we'll be able to measure it and apply that reading to make irrigation decisions.
okay, cool. And then he's somewhat calling you out here when you were showing off those new soil sensors for the green walls. Um,
Mm-hmm.
he said that nobody sold him those ones, so we're just calling you out a little bit. Maybe those are super new,
They
but
are. They are.
okay, cool.
They're available for order now, and we're expecting to fulfill orders by the middle of February.
There you go. So Daryl, you can't get too mad that they didn't sell them to you. So go pick them up now. Um, so there's a couple other ones in regards to going back to the green roof stuff a little bit. Uh, Daryl actually had another question about how many sensors you actually did have on the Facebook roof,
Okay.
and are they operating valves or are they just used for measurement? And then if if they are operating valves, do each one of those have to be calibrated to their location?
Okay. Good questions. So the control system that is installed on that green roof is able to support 25 soil moisture sensors on the two-wire path. And the designer actually designed it to support 25 soil moisture sensors. So the controller is maxed out on the number that it can support on that green roof. And they are planted throughout the green roof based on hydrozones that are occurring across the installation. Those hydrozones are based on plant material primarily, or sprinkler type. So those sensors are buried in representative zones within those hydrozones, and then they are set up to control the frequency of irrigation of those different zones within that hydrozone, and then any like zones to that zone where the sensor is buried is linked to that sensor within that hydrozone, if that makes sense. So one sensor is able to control several different irrigation zones that are like hydrozones of the zone where the sensor is buried.
Okay, cool. I think that explains that pretty well. Now, Brendan had a similar question as far as for green roofs. Um, for that moisture sensing, is there a general depth that the sensor needs to be at? They've done stuff that requires 6-inch depth, which made it sit actually on top of a capillary mat. So that mat actually retained more of that moisture, so they were getting unusual run times. So is there maybe a general rule of depth or something you can explain there a little bit?
Absolutely. So, uh, in our specification for sensor uh, installation, we uh, specify that the sensor get installed in the top 1/3 of the active root zone of the plant material that it is monitoring. So if we look at the plant water use characteristics, most of the effective root zone of that plant is right below the crown of the plant material itself. And that's where the active uh, roots are that uptake water for the plant. And then, of course, you've got deeper roots, which are anchor and then also act as, drought um, type roots that will obtain water from deeper in the profile. So, um, when you're dealing with a mat that's being used underneath and relying on the capillary action to move upward to the active roots of the plant material, you're still wanting to uh, bury it at that shallower depth so that you're able to see how much water is available to those feeding roots of that plant material. So typically in turf grass, we recommend the sensor get buried at a 3 to 4 inch depth below the crown of the turf grass. In shrubs or trees, they could be buried deeper, but we want the sensor buried at a depth where it can effectively see an application of water in that primary root zone area where the plant is uptaking water out of the soil profile.
That makes sense. We do have one question about somebody wants to know a little bit about mulching that is done to prevent moisture loss. Do you suggest a type or how often that should be replenished? Is there a benefit to that with the soil sensors and stuff?
Well, obviously, if you're going to be mulching, the soil that the plant material is planted in, you're going to have less evaporative effects, which we will be able to account for with the soil moisture sensor because, again, we're seeing in real time how much evaporation is occurring out of that soil profile. So, depending on the part of the country or the region and the predominant mulch type that is utilized, regardless of what mulch is used, we'll be able to see the benefits of that mulching because more water will be held longer in that soil profile and may um, eliminate uh, the frequency of irrigation requirements that may be necessary.
Got it. Cool. We do have one from Bill, and this is goes along with what you explained with the top 1/3 placing that actual soil sensor. But if you do have different hydrozones with plants with all those differing root depths, what depth should you place that sensor? And does that sensor measure moisture at the different depths?
Okay, so our standard moisture sensor has a 18-inch blade um, that we average the moisture reading across that blade profile. So if in shrub or a tree application where you're burying it deeper, you know, we may see this sensor installed at an angle, so we get a more indicative moisture content reading across that um, deeper profile. So in turf grass, we like to see them installed, horizontal to grade at 3 to 4 inches. In shrub or tree applications, you may angle them at a 30 or 45-degree angle to get a better indication of how much moisture is available to that root zone at varying depths across that root ball.
All right. And then I think we got one more here. This is Daryl again. He's saying the problem that he has with the green wall condition, using the sensor, is that the sensor only reads a small part of the wall, and the moisture profile is a little sporadic in a fabric wall. So the question is, could you link multiple sensors and adjust the readings to an average so you're not basing your watering on just one spot?
No. So
Right.
the sensors act independently in conjunction with the programs or the zones that they're assigned to. So having the ability to uh, you know have multiple readings and take that into account in the programming and the controller itself, we're limited in that regard. Um, but again, the sensors being used primarily to give the manager a good indication of what moisture is available in that green wall panel at any given time. So, and a lot of it would depend also on how the irrigation zones are uh, designed in that panel as well. Um, the more irrigation zones that are designed into the panel, the more sensors that could be used to give a good indication of the variation across the given panel.
All right. Well, cool. That seems like it was all. We are going to be cutting off a little early today, which is always a plus. So you guys can get on with your day. But again, Chris, thank you so much for presenting this stuff. It's really, really interesting and really helpful to see the inner workings of it. So if you guys at all have any questions, definitely reach out to Chris or reach out to us and we can pass questions along. But with that being said, enjoy your weekend and we'll talk to you next week.
Thank you very much, Jake.